In the quiet solitude of a clear night, humanity has always looked up and wondered. The stars, scattered like diamond dust on black velvet, have been our companions through millennia of history, our guides, our gods, and our greatest mystery. They seem to whisper of infinity, of a grandeur so immense that our terrestrial concerns shrink into insignificance. For most of human existence, this celestial tapestry was just that, a beautiful, unchanging backdrop to our lives. But in the last century, our understanding has undergone a revolution so profound, it has reshaped our very definition of reality. We have learned that the sky is not a static ceiling, but a vast, dynamic ocean of time and space, and that every point of light is a message from a distant past. We have begun to chart this cosmic ocean, to measure its depths and map its shores. We have given a name to the portion we can access, the observable universe. This is not a boundary of matter or a physical wall at the end of space. It is a horizon of perception, a sphere of information drawn around us, limited not by the size of the universe itself, but by the finite speed of light and the finite age of time. Everything we have ever seen, every galaxy ever photographed, every star ever studied, resides within this bubble. But the most tantalizing question, the one that drives cosmology forward, is not about what lies within our view, but what lies beyond it. This is a journey to the edge of what is knowable, to the cosmic horizon, where the light from the beginning of time is just now reaching us, and where the greatest secrets of existence await. To understand the scale of our universe is to first grapple with its fundamental messenger, light. We perceive light as instantaneous. We flip a switch, and a room is illuminated. But this is an illusion born of our planetary scale. In cosmic terms, light is a diligent but plodding traveler. It moves at the ultimate speed limit, approximately 300,000 kilometers per second, but the distances it must traverse are so astronomical that its journeys can take billions of years. This simple fact has a staggering implication. When we look out into space, we are looking back in time. The light from our own sun takes over 8 minutes to reach us. We see the sun not as it is now, but as it was 8 minutes ago. The light from Proxima Centauri, our nearest stellar neighbor, is a 4-year-old message. The faint ghostly glow of the Andromeda galaxy, our closest major galactic neighbor, is an image of that galaxy as it was 2.5 million years ago, when our own ancestors were just beginning their evolutionary journey on the African savanna. Every telescope, from a backyard amateur scope to the mighty James Webb Space Telescope, is a time machine. The deeper they peer into space, the further they look back into the cosmic past. This allows us to witness cosmic history firsthand. We can see galaxies in their infancy, colliding and merging to form the grand spirals we see today. We can see the first generations of stars igniting, forging the heavy elements that would one day make planets and life possible. We are not just observing a static universe. We are watching a 13.8 billion-year-old story unfold. But how do we measure these unimaginable distances? How can we confidently say a smudge of light is billions of light years away? Astronomers have developed a sophisticated toolkit known as the Cosmic Distance Ladder, where each rung allows us to measure further into the void. For nearby stars, we use parallax, the same effect you see when a nearby object appears to shift against a distant background as you move your head. By measuring this tiny shift in a star's position as the Earth orbits the Sun, we can triangulate its distance. For greater distances, this method becomes impractical. So we turn to standard candles, astronomical objects that have a known intrinsic brightness. One of the most crucial are Cepheid variable stars, which pulse at a rate directly related to their luminosity. By measuring the pulse, we know how bright the star truly is. By comparing this to how bright it appears from Earth, we can calculate its distance. It's like seeing a 100-watt light bulb in the distance. The dimmer it appears, the farther away it must be. For the truly vast intergalactic distances, we rely on an even brighter standard candle, type Ia supernovae. These are the spectacular explosions of white dwarf stars in binary systems. They occur when the star reaches a precise critical mass, meaning they all explode with almost the exact same peak luminosity. These cataclysmic events are so bright, they can briefly outshine their entire host galaxy, making them visible across billions of light years. They are the ultimate cosmic lighthouses, allowing us to map the universe on its grandest scales. It was by observing these distant supernovae that we made one of the most shocking discoveries in the history of science. In the late 1990s, two independent teams of astronomers found that these distant explosions were dimmer and therefore farther away than they should have been based on the prevailing models of the cosmos. The universe was not just expanding, as Edwin Hubble had discovered decades earlier. Its expansion was accelerating. Some mysterious repulsive force was pushing everything apart, faster and faster over time. We have named this force dark energy, and it remains the single greatest puzzle in physics. This accelerating expansion has profound consequences for the size of our observable universe. A common misconception is that if the universe is 13.8 billion years old, then the edge of what we can see must be 13.8 billion light years away. But this fails to account for the stretching of space itself. Imagine a photon of light emitted from a distant galaxy shortly after the Big Bang. As it travels towards us, the very fabric of space-time between us and that galaxy is expanding. It's like an ant trying to walk along a rubber band that is being stretched. The ant is moving forward, but its destination is moving away even faster. The light from the most distant objects we can see has been traveling for nearly 13.8 billion years. But during that immense journey, the space it was crossing has expanded dramatically. The point from which that light was emitted is now, today, estimated to be about 46.5 billion light years away from us. This means our observable universe is not a sphere with a radius of 13.8 billion light years, but one with a radius of 46.5 billion light years. The total diameter is a mind-numbing 93 billion light years. This is the boundary of our sight, our cosmic horizon. Any light from an object beyond this distance, emitted 13.8 billion years ago, has simply not had enough time in the entire history of the universe to reach us yet. At the very edge of this horizon, we find the oldest light in the universe, the cosmic microwave background, CMB. This is not light from a star or galaxy, but the faint residual afterglow of the Big Bang itself. For the first 380,000 years of its existence, the universe was a super-hot, dense, opaque plasma of protons, neutrons, and electrons. Light could not travel freely. Photons were constantly scattered by charged particles, trapped in a cosmic fog. But as the universe expanded and cooled, a critical moment was reached, an event called recombination. Electrons combined with nuclei to form the first neutral atoms. Suddenly, the universe became transparent. The photons that were present at that exact moment were finally set free, and they have been traveling across the cosmos ever since. Today, we detect this ancient light as a faint, uniform microwave hiss coming from every direction in the sky. It is the baby picture of our universe, a snapshot of the cosmos when it was just a newborn. The tiny temperature fluctuations in the CMB, variations of just a few parts per million, are the primordial seeds from which all future structure would grow. They represent the slight density differences in the early universe that, under the relentless pull of gravity over billions of years, would blossom into the galaxies, clusters, and superclusters we see today. The CMB is the ultimate wall for our telescopes. We can't see past it with light because we are looking at a time when the universe itself was opaque. As we survey the contents of our 93 billion light-year bubble, we find it is not a random assortment of galaxies. On the largest scales, matter has organized itself into a breathtakingly beautiful and complex structure known as the cosmic web. This web is a vast, interconnected network of matter spanning the entire observable universe. It consists of dense filaments, like cosmic superhighways, along which galaxies flow like rivers of light. Where these filaments intersect, they form massive knots, the great galaxy clusters and superclusters, cosmic cities teeming with thousands of galaxies, each containing hundreds of billions of stars. Our own Milky Way galaxy is part of the local group, a modest collection of about 50 galaxies. This group, in turn, is on the outskirts of the Virgo supercluster, which itself is just one lobe of an even grander structure we have named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea contains over 100,000 galaxies and stretches for more than 500 million light-years. And yet this colossal structure is just one of countless superclusters that populate the cosmic web. Connecting these luminous structures are the voids, immense, nearly empty expanses of space. These cosmic deserts, such as the Buddha's void, can be hundreds of millions of light-years across, containing very few, if any, galaxies. They are the stark, silent counterpoint to the glittering filaments and clusters. The universe, it seems, is mostly empty space, with all the beauty and complexity concentrated along the gossamer threads of this cosmic tapestry. But there is a profound problem. When we calculate the mass of the galaxies and clusters based on the stars and gas we can see, the numbers don't add up. The gravitational pull is far stronger than the visible matter can account for. Galaxies are spinning so fast they should have flown apart billions of years ago. Clusters of galaxies are held together by a gravitational grip that visible matter alone cannot provide. There must be something else there, something invisible, something that does not emit, absorb, or reflect light. We call it dark matter. Dark matter is the invisible scaffolding of the universe. Computer simulations show that without it, the tiny density fluctuations in the cosmic microwave background would not have had enough gravitational pull to coalesce into the vast cosmic web we see today. Dark matter provides the gravitational foundation, creating deep wells into which normal matter falls, eventually igniting to form stars and galaxies. It is the silent architect of the cosmos, shaping the universe on its grandest scales, yet its true nature remains a complete enigma. We know it's there from its gravitational effects, but we have never directly detected a single particle of it. If dark matter is the universe's hidden skeleton, then dark energy is its phantom heart, pumping the cosmos apart at an ever-increasing rate. Together, these two mysterious components dominate the universe's energy mass budget. Our latest measurements, primarily from the CMB and distant supernovae, paint a humbling picture of reality. All the matter we know and understand, every star, planet, asteroid, gas cloud, and living being, accounts for a mere 5% of the universe. Approximately 27% is the mysterious dark matter, the invisible glue holding it all together. And the vast remainder, a staggering 68%, is the even more mysterious dark energy, the repulsive force driving the accelerating expansion. We are, in essence, strangers in our own universe. We have mapped a vast cosmic ocean, only to discover that 95% of it is made of something we cannot see and do not comprehend. Our physics, so successful at explaining our world, breaks down when confronted with the two dominant constituents of the cosmos. This is not just a small gap in our knowledge. It is a chasm of ignorance that points towards a new, more fundamental understanding of reality that is yet to be discovered. This brings us to the ultimate question, the one that lingers at the edge of our cosmic horizon. What lies beyond the 93 billion light-year sphere of our observable universe? Science cannot give a definitive answer, as we have no way to receive information from that region. By definition, it is beyond our observational reach, but based on what we do know, we can make some powerful and logical extrapolations. The simplest and most widely accepted idea is based on the cosmological principle, the assumption that our location in the universe is not special or privileged. Just as the Earth is not the center of the solar system and the Sun is not the center of the galaxy, our observable universe is likely not the center of the entire universe. If this principle holds true on the largest scales, then the region beyond our horizon is probably just more of the same. More voids, more filaments, more superclusters, stretching on and on, populated by an endless tapestry of galaxies. The geometry of our universe appears to be flat. Observations of the cosmic microwave background show that on the largest scales, space-time does not curve back on itself. A flat universe, if it is not finite, is infinite. If the universe truly extends forever, then the implications are almost too profound to grasp. In an infinite universe, every possible event with a non-zero probability must occur, and not just once, but an infinite number of times. Somewhere out there, in a region of space so distant we will never see it, there could be another observable universe bubble, identical to ours in every conceivable way. In another, even more distant region, there could be a version of you reading this very text, but one who made a different choice for breakfast this morning. And further still, a version of humanity that never evolved, on a planet Earth that orbits a different star. This is the staggering, almost philosophical consequence of a truly infinite cosmos, the statistical certainty of infinite repetition and variation. Other, more speculative theories propose even stranger possibilities. The theory of eternal inflation suggests that our Big Bang was not a one-time event. Instead, our universe may be just one bubble in a much larger multiverse, where new universes are constantly budding off and expanding. Each of these bubble universes could have its own unique physical laws, its own fundamental constants, perhaps even a different number of dimensions. In this cosmic foam of universes, some might be stillborn, collapsing back on themselves in an instant. Others might be barren, with laws that do not permit the formation of stars or complex chemistry. And some, like our own, might be just right for the emergence of complexity and life. We stand on the shore of a cosmic ocean, our knowledge a single grain of sand. We have built remarkable tools to extend our senses, to capture light that has traveled for eons, and to piece together the grand narrative of our cosmic origins. We have mapped our local shores, this observable bubble we call home. We understand its contents, its structure, and its history with breathtaking precision. Yet, with every answer we find, the horizon of our ignorance only seems to expand. The discovery of dark matter and dark energy revealed that the universe we thought we knew was merely the tip of a cosmic iceberg. The light that defines our horizon is still traveling. The universe continues its relentless, accelerated expansion. Galaxies beyond a certain distance are now receding from us faster than the speed of light, not because they are breaking the laws of physics, but because the space between us and them is expanding that quickly. We will never see the light they emit from this moment forward. They have been carried away by the cosmic tide, their futures forever beyond our reach. Our observable universe, while vast, is only a finite, shrinking fraction of what we could ever hope to see. The night sky of the far future will be a much darker, lonelier place, with most galaxies having receded beyond our cosmic horizon, leaving our own local group of galaxies isolated in an immense, empty void. We are living in a privileged moment in cosmic history, a time when the universe is still young and bright enough for us to piece together its story. But the ultimate truth may forever lie beyond our grasp. The universe beyond our horizon may be infinite and filled with wonders beyond our imagination, or it may be something else entirely, something for which we do not yet have the language or the mathematics to describe. The one certainty is that the quest for knowledge will drive us to keep looking, to keep questioning, and to keep pushing against that fundamental boundary of light and time. The greatest mysteries are not found in the darkness between the stars, but in the silent, unending expanse that lies forever beyond the edge of our sight. This silent, unending expanse that lies forever beyond the edge of our sight is more than just a physical void. It is a conceptual one. It forces us to confront one of the most profound puzzles in modern cosmology, a puzzle that is hidden not in the distant darkness, but in the very light that fills our sky. The cosmic microwave background, that beautiful baby picture of our universe, presents a deep conundrum known as the horizon problem. When we look at the CMB in one direction of the sky and then turn our telescopes to the completely opposite direction, we find that the temperature of this ancient radiation is astonishingly uniform, to within 1 part in 100,000. On the surface, this might not seem surprising. One might assume the early universe was a hot, well-mixed soup, and everything naturally reached the same temperature. But the problem lies in the finite speed of light. At the time the CMB was emitted, 380,000 years after the Big Bang, the two opposite points in our sky that we observe today were already separated by a vast distance, nearly 90 million light-years. According to the standard model of cosmic expansion, there simply had not been enough time in the entire history of the universe for these two regions to ever have been in causal contact. No light, no heat, no information of any kind could have traveled from one to the other to average out their temperatures. They should have had no knowledge of each other's existence. It would be like finding two people on opposite sides of the Pacific Ocean who have never met or communicated, having the exact same body temperature down to 1,000th of a degree. It defies logic. So why is our universe so smooth? Why is it so uniform on the largest scales? The most compelling and widely accepted solution to this puzzle is a theory known as cosmic inflation. This theory posits that in the very first fraction of a second after the Big Bang, a sliver of time so infinitesimally small it is almost beyond human comprehension, lasting from perhaps 10 to the minus 36 seconds to 10 to the minus 32 seconds, the universe underwent a period of violent exponential expansion. The fabric of space itself stretched at a rate far faster than the speed of light, swelling from a size smaller than a proton to something at least as large as a grapefruit, and likely unimaginably larger. Inflation elegantly solves the horizon problem. Before this hyperexpansion began, the entirety of what would become our observable universe was an incredibly tiny, subatomic patch. In this minuscule volume, all parts were in close causal contact and had plenty of time to reach a state of thermal equilibrium, smoothing out any initial temperature differences. Inflation then took this tiny, smooth, uniform region and stretched it to colossal proportions. The uniformity we see in the CMB today is therefore a fossilized remnant of the uniformity that existed on a quantum scale before inflation began. We are, in effect, looking at a magnified image of a single, quantum fluctuating patch from the dawn of time. This idea is not mere speculation. The theory of inflation makes specific, testable predictions. It predicts that the geometry of the universe should be almost perfectly flat, which is exactly what our precise measurements of the CMB have confirmed. More impressively, it predicts the precise statistical pattern of the tiny temperature variations, or anisotropies, that we see in the CMB. These minute ripples are not random noise. They are the result of quantum fluctuations in the primordial energy field that drove inflation, stretched to astronomical sizes. When space probes like WMAP and Planck mapped the CMB in high resolution, the patterns they found matched the predictions of inflation with stunning accuracy. It was a triumphant moment for cosmology, providing powerful evidence that this almost unbelievable period of hyperexpansion truly happened. But the theory of inflation opens a door to an even more staggering concept. The quantum field that drove inflation, often called the inflaton field, may not have decayed and ended its expansion everywhere at the same time. According to the model of eternal inflation, while inflation ended in our region of space, allowing our universe to form, it likely continued in other, more distant regions, and it may still be continuing today. This paints a picture of a multiverse on a truly cosmic scale. Our entire 93 billion light-year observable universe might be just one bubble, one pocket universe in an infinitely vast, eternally inflating metaspace. In this larger reality, other bubbles are constantly forming, each one undergoing its own Big Bang and expanding into a new universe. Our universe is not a unique event, but just one of an infinite number of blossoms on an eternal cosmic tree. If this is true, these other universes could be wildly different from our own. The random nature of quantum mechanics during inflation could mean that the fundamental laws and constants of physics are different in each bubble. One universe might have a much stronger force of gravity, causing it to collapse back on itself moments after its birth. Another might have different elementary particles or even a different number of spatial dimensions. The vast majority of these universes would likely be sterile and empty, completely inhospitable to the formation of complex structures like galaxies, stars, or life. This idea of a multiverse provides a potential, if controversial, explanation for another deep cosmic mystery, the fine-tuning problem. As physicists have delved deeper into the laws of nature, they have found that many fundamental constants appear to be exquisitely tuned to values that permit the existence of a complex universe. If the strong nuclear force which binds protons and neutrons in atomic nuclei were just a few percent weaker, only hydrogen would exist. No heavier elements, no carbon, no life. If the cosmological constant, the value representing the density of dark energy, were even slightly larger, its repulsive force would have torn the universe apart before any galaxies could form. Its value is so precise, it has been compared to hitting a 1-inch target from the other side of the observable universe. Why are these values so perfect? One possibility is sheer luck. The constants are what they are, and we just happen to live in a universe where they are right. Another is that a yet unknown theory of everything will one day show that these values are not arbitrary, but are mathematically required to be what they are. But the multiverse offers a third, compelling explanation through the anthropic principle. The principle states that our observations of the universe are inherently biased by the fact that we exist to observe it. If there are an infinite number of universes, each with a random set of physical constants, then it is no surprise that we find ourselves in one of the very rare universes where the constants are compatible with life. We couldn't exist in any of the others to wonder why they are so barren. Our existence acts as a selection filter, picking out one of the habitable universes from an infinite sea of sterile ones. In this view, the fine-tuning is not a miracle, but a statistical inevitability. The cosmic horizon, then, takes on a new meaning. It is not just a boundary of sight, but potentially the edge of our own physical reality, our specific bubble of space-time with its unique set of laws. The physics beyond our horizon might not just be more of the same, but fundamentally and incomprehensibly different. This concept of a boundary of information finds a fascinating parallel in another of the universe's great mysteries, the black hole. A black hole's event horizon is also a boundary of no return. Just as light from beyond the cosmic horizon cannot reach us, anything that crosses the event horizon of a black hole, including light, can never escape. Both are one-way membranes in space-time, defining the limits of a causally connected region. This connection has led theoretical physicists to explore a radical and mind-bending idea known as the holographic principle. It emerges from studying the thermodynamics of black holes, where it was discovered that the maximum amount of information that can be contained within a region of space is not proportional to its volume, but to the surface area of its boundary. This is deeply counterintuitive. It's as if all the data on a hard drive was stored not throughout its volume, but only on its two-dimensional outer casing. Extrapolating this to the entire cosmos, the holographic principle suggests that our entire three-dimensional universe, everything we see and experience, might be a holographic projection of information stored on a two-dimensional surface at its boundary. This boundary could be the cosmic horizon itself. In this view, the reality we inhabit, with its apparent depth and complexity, could be the decoded output of a more fundamental, lower-dimensional reality written on the edge of space and time. This is a speculative frontier of physics, but it is one that is rigorously pursued because it offers a potential path to unifying quantum mechanics and general relativity, the two great pillars of modern science that stubbornly refuse to work together. It redefines what we mean by space, and reality, suggesting that the universe's deepest secrets are not hidden in its voluminous depths, but are encoded on its most distant boundary. Our journey to the edge of the observable universe has led us on an unexpected path. We began by trying to map our cosmic neighborhood and ended by questioning the very foundations of reality. The cosmic horizon is not a destination we can ever reach, but rather a constant companion on our intellectual journey. It is a mirror reflecting the limits of our knowledge and the scale of our ambition. Each layer of understanding has only revealed a deeper, more profound mystery. The mapping of galaxies led to the discovery of cosmic expansion. The measurement of that expansion revealed the enigma of dark energy. The study of galaxy dynamics unveiled the ghost of dark matter. The uniformity of the universe's afterglow pointed to a period of unimaginable inflation. And inflation, in turn, opened the door to the possibility of an infinite multiverse, a concept that challenges our very definition of universe. We are suspended in a cosmic moment, armed with instruments that can decipher the story written in starlight from 13.8 billion years ago. We have built a coherent, evidence-based narrative of our origins, from a quantum flicker to a cosmos teeming with 1 trillion galaxies. Yet this entire narrative, this vast and wondrous story, may only be the prologue. The true scope of reality, the full extent of what is, may extend infinitely beyond the faint ancient light that currently marks the boundary of our perception. The quest is no longer just about discovering more stars or galaxies. It is about understanding the fundamental grammar of existence and whether the book of the cosmos has an infinite number of pages. The quest is no longer just about discovering more stars or galaxies. It is about understanding the fundamental grammar of existence and whether the book of the cosmos has an infinite number of pages. For centuries, we have read this cosmic story using a single language, light. From visible photons to radio waves and X-rays, the electromagnetic spectrum has been our sole messenger, carrying tales of distant suns and nascent galaxies. But we are now on the cusp of a new era of discovery, an age where we are learning to decipher other, more elusive cosmic languages. This is the dawn of multi-messenger astronomy, a new chapter in our exploration that promises to reveal aspects of the universe that have forever been hidden from the gaze of our light-based telescopes. The new cosmic messengers. The first of these new languages is perhaps the most profound, gravity itself. According to Einstein's theory of general relativity, space and time are not a static backdrop, but a dynamic, interwoven fabric called space-time. Massive objects warp this fabric, and when they undergo extreme acceleration, such as when two black holes or two neutron stars spiral into each other and merge, they create ripples in space-time, much like two colliding boats create waves in a pond. These ripples are gravitational waves. For a century, they were purely theoretical, but on September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history. Its two detectors, separated by thousands of kilometers, registered a fleeting, infinitesimally small vibration, a stretching and squeezing of space-time itself by a distance less than 1/10,000th the diameter of a proton. This tiny signal was the echo of a cataclysmic event that had occurred 1.3 billion years ago, the violent merger of two black holes. For the first time, humanity had not seen the universe, but had felt it. Gravitational waves are a revolutionary tool because they are not light. They are not blocked or distorted by the vast clouds of gas and dust that obscure our view of many cosmic phenomena, such as the core of our own Milky Way galaxy. They travel to us almost completely unimpeded, carrying pristine information directly from the heart of the most violent events the universe has to offer. They are allowing us to see the invisible. We have detected the mergers of binary black holes, objects that emit no light and are otherwise undetectable. We have witnessed the collision of neutron stars, an event that not only generated gravitational waves but also a firework display across the entire electromagnetic spectrum, from gamma rays to radio waves. This single event, detected in 2017, confirmed that these mergers are the primary cosmic forges for many of the heaviest elements in the universe, including the gold and platinum in our jewelry. We are quite literally wearing the remnants of ancient cosmic collisions. The future of gravitational wave astronomy promises to unveil even deeper secrets. Future space-based observatories like LISA, the Laser Interferometer Space Antenna, will consist of 3 spacecraft flying in a triangular formation millions of kilometers apart. This immense scale will make it sensitive to much lower frequency gravitational waves, those produced by the mergers of supermassive black holes at the centers of galaxies, or perhaps even the faint residual hum of primordial gravitational waves created during the inflationary epoch itself. Detecting this primordial background would be the ultimate confirmation of cosmic inflation, providing a direct window into the first moments of the universe's existence, a time far beyond what the cosmic microwave background can show us. A second cosmic messenger is the elusive neutrino. These are fundamental particles, often called ghost particles, that are produced in abundance in the nuclear furnaces of stars and in violent events like supernovae. They have almost no mass and no electric charge, meaning they interact incredibly weakly with other matter. A single neutrino could pass through a light year of solid lead with a good chance of not hitting anything. While this makes them incredibly difficult to detect, it is also their greatest strength. Trillions of neutrinos from our sun pass through your body every second, unnoticed. But vast detectors, like the IceCube Neutrino Observatory, buried deep within the Antarctic ice, use a cubic kilometer of pristine ice as their detection medium. When a high-energy neutrino from a distant cosmic source happens to strike an atom in the ice, it produces a tiny flash of blue light that can be detected by thousands of sensitive sensors. By tracing the path of this light, scientists can determine the direction from which the neutrino came. In 2018, IceCube traced a high-energy neutrino back to its source, a blazar, a supermassive black hole at the center of a distant galaxy that was spewing a jet of particles towards Earth at nearly the speed of light. It was a landmark achievement, marking the first time a source of high-energy cosmic neutrinos had been definitively identified. Neutrinos offer a unique complementary view of the high-energy universe. While gamma rays can be blocked or scattered, neutrinos travel in a straight line from their source, carrying direct information about the nuclear processes that created them. They are helping us to peer directly into the cores of exploding stars and the hearts of active galactic nuclei, providing crucial clues about the physics that governs the most extreme environments in the cosmos. The next generation of eyes. While these new senses are revolutionizing our understanding of cosmic cataclysms, our oldest tool, light, is about to enter its own golden age. A new fleet of ground and space-based telescopes is poised to map the universe with unprecedented depth and precision, designed specifically to tackle the monumental questions of dark matter and dark energy. The James Webb Space Telescope, JWST, is already transforming our view of the early universe. By observing in the infrared, it can pierce through cosmic dust and look back to an epoch just a few 100 million years after the Big Bang, capturing the light of the very first stars and galaxies as they ignited in the primordial darkness. Each image from JWST is a journey back in time, revealing the building blocks of galaxies like our own in their infancy and testing our models of cosmic evolution at their very limits. Soon to join the quest is the Nancy Grace Roman Space Telescope. While telescopes like Hubble and Webb provide stunningly deep but narrow views of the cosmos, Roman will do the opposite. It will have a field of view 100 times larger than Hubble's, allowing it to survey vast swaths of the sky with incredible speed and detail. Over its mission, It will image billions of galaxies and discover thousands of supernovae. This colossal dataset will be used to map the geometry of space-time and the distribution of dark matter through a technique called weak gravitational lensing, measuring the tiny distortions in the shapes of distant galaxies caused by the gravity of unseen dark matter in the foreground. On the ground, the Rubin Observatory in Chile will undertake the most ambitious sky survey ever attempted. Over 10 years, its Legacy Survey of Space and Time, LSST, will photograph the entire visible southern sky every few nights, creating a time-lapse movie of the universe. It will catalog more stars and galaxies than there are people on Earth. It will track billions of objects, charting the expansion history of the universe with exquisite precision by monitoring distant supernovae and creating the most detailed map of the cosmic web and its dark matter scaffolding ever produced. These observatories will not provide a single eureka moment answer to the nature of dark energy and dark matter. Instead, they will provide vast, high-precision data sets that will allow scientists to test competing theories with statistical rigor. Is dark energy a constant property of space, Einstein's cosmological constant, or does its strength change over time? Is dark matter a single undiscovered particle, or is it something more complex? By mapping the universe's past and present structure in such detail, we can begin to narrow down the possibilities and close in on the truth. The search within and without. The quest to understand the cosmos is not just an outward journey, it is also an inward one. The greatest mysteries of cosmology, dark matter, dark energy, and the physics of the Big Bang are inextricably linked to the deepest questions of particle physics. The universe on its largest scale is governed by the laws of the very small. This is why some of the most important cosmological experiments are not on mountaintops, but deep underground. In shielded laboratories, experiments like Lux Zeppelin, LZ, and Xenont use giant vats of liquid xenon to try and catch the fleeting interaction of a dark matter particle with a normal atom. A successful detection would be one of the most important discoveries in the history of science, finally revealing the identity of the universe's invisible mass. At the same time, particle accelerators like the Large Hadron Collider, LHC, at CERN, are recreating the conditions of the early universe on a microscopic scale. By smashing protons together at nearly the speed of light, physicists are searching for new particles and forces that are not described by our current standard model of particle physics. It is possible that the LHC could produce and detect dark matter particles in its collisions, or uncover evidence of new physical principles, like supersymmetry, that could explain some of the universe's lingering mysteries. The connection is profound. The energies of the LHC probe the universe as it was in the first trillionth of a second, a time when the fundamental nature of dark matter and the forces of the universe were being forged. Conclusion. Our place in the known. We began our journey looking up at a sky of seemingly disconnected points of light. We have traveled across 93 billion light-years of space and 13.8 billion years of time. We have discovered a universe of unimaginable scale and complexity, woven together by invisible matter and pushed apart by an unknown energy. We have learned that our reality may be just one bubble in an infinite multiverse, and that the solid world around us might be a holographic projection of information stored at the edge of time. With every new discovery, the universe has become both grander and more mysterious. We have answered the ancient question of where are we, with a map so vast it defies true comprehension. We reside on a small planet orbiting an average star in a typical galaxy that is just one of hundreds of billions within our observable horizon. We are cosmically insignificant in scale, yet we are also profoundly special. For it is here, on this pale blue dot, that the universe has developed a way to be aware of itself. The human mind, a product of billions of years of cosmic and biological evolution, is now capable of deciphering the light from creation's dawn, of feeling the tremors in space-time from colliding black holes, and of formulating theories that describe the universe's first moments. Our quest for knowledge has transformed us from passive spectators into active participants in the cosmic story. The cosmic horizon remains. It is a fundamental boundary, a reminder of our limitations. There are parts of reality we may never see, questions we may never definitively answer. And yet, this is not a cause for despair, but for inspiration. It is the existence of this horizon of the unknown that fuels our curiosity, drives our ingenuity, and gives meaning to our search. The 95% of the cosmos that remains dark and mysterious is not an empty void in our knowledge, but a vast and fertile landscape for the next generation of explorers to chart. We look up at the night sky today with a different kind of wonder than our ancestors did. It is a wonder deepened by knowledge, tempered by the humility of what we do not know, and ignited by the promise of what we might yet discover. We look up, not just in awe, but with purpose. For in the story of the universe, we have discovered a breathtaking truth. We are not merely the readers. We are the consciousness through which the cosmos begins to know itself.